Yep, that's looking good. Welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night by Zoom 50 times a year. Tonight it's my pleasure to introduce to you Reid Van Lehn. He's a professor in the Department of Chemical and Biological Engineering here at UW-Madison, and he's with the Chemical Upcycling of Waste Plastics program. Reid, I'm going to ask you the 5 questions. Where were you born?
Pittsburgh, Pennsylvania.
Pittsburgh, Pennsylvania. And where'd you go to high school?
I went to a school called Shadyside Academy.
And then where'd you go for your undergrad and what did you study?
Yeah, so I went up to MIT in Cambridge, Mass, and was a materials scientist there.
And then where'd you go for your master's or PhD or both?
Yeah, so I stuck around Cambridge. I moved departments and then did a PhD also at MIT.
And then did you do any postdocs or did you come directly here to UW?
I did do a postdoc. I decided to go all the way across the country to Caltech to do a postdoc in sunny California.
And then you decided the ice fishing was better in Madison.
Yeah, I just wanted to split the difference and end up in Madison. Right?
Yes. And when did you arrive here?
2016.
Very good. Well, thank you very much for speaking with us tonight about new recycling technologies to combat plastic pollution. I hope everybody will join me in welcoming Reid Van Lehn to Wednesday Night at the Lab. Reid, go ahead and take it away.
Great. All right. Thank you so much, Tom. Thank you for the introduction and thank you for having me. It's a pleasure to be here to speak about some of the research and really some of the background about plastic waste recycling that I can share with you as part of my affiliation with the new Center for the Chemical Upcycling of Waste Plastics. This is a new center we're really excited about here on campus. It's been funded by the Department of Energy for the next 5 years as part of really a nationwide effort to combat plastic pollution. So in this talk, I'll tell you a little bit about what we're doing and also what people are doing in academic and industrial labs across the country. So probably many of you are aware of some of the many news articles that have been focused on the plastic pollution problem over the last few years. Some of these more positive, some of these more negative. So here I've sort of shown a subset of each, some articles pointing out the fact that maybe plastic recycling is not all that it's cracked up to be, some using the term that it's a scam. Others focusing on new technologies, these infinite plastics, and some of the new technologies being developed in groups like ours to address these problems. I particularly want to point out a PBS NewsHour program that was aired just a couple of weeks ago. If you go back and watch that, you would actually see interviews with 2 UW-Madison faculty. So it's a really exciting time to be in the plastic recycling field because there's a lot of interest in this area for a very particular reason that I'll talk about a few slides from now. So my goal with this talk is to both tell you a little bit about the plastic waste challenge, the scale of plastic waste, and some of the background material to help you understand maybe the left-hand side of the slide, as well as some of the technologies that we're developing here at UW and elsewhere that sort of informs you about the right-hand side of this slide. So I'll really divide this talk into 3 major parts. The first part will be telling you some of the background about plastic production. What are plastics? Where are they? What materials are they made out of? And the challenges that we have with our existing recycling infrastructure that really makes it difficult to avoid issues like this, which is massive plastic accumulation in landfills. In the second part of my talk, I'll tell you about some of the research that we're doing as part of this center, which we call CUP, in terms of both our near-term goals, our long-term goals, and 2 of the key technologies that we're trying to develop and hopefully bring to market in the not-too-distant future. And then briefly at the end of my talk, I'll highlight some other exciting technologies being developed that have a slightly longer time scale to adoption, but could really change the face of plastic recycling. So to start us off, let's just make sure we're all on the same page by defining some key terminology. So first, what is a plastic? Well, if you talk to a chemist, they'll probably talk to you about plastics in terms of their molecular constituents, which are called polymers. Polymers are called chain molecules because I can think of a polymer as repeating a single small molecule monomer millions of times. Okay, so this is polyethylene, where each of these red dots is a carbon atom. This is formed by chemically linking together many of these ethylene monomers. So these are also called macromolecules because they're so large. So this is a polymer. If I were to talk to somebody in the plastic industry, they would probably instead refer to this material as a resin. A resin is typically what we refer to when we call plastics by their bulk material name. Resins are used to make plastics. Now, the means by which we process resins into plastic products can differ, and I won't talk about that a lot here. The main point is at the end of the day, I convert all these resins into a wide variety of products. Probably all of you are within a foot of something made out of plastic, particularly if you're sitting at a computer right now. These are ubiquitous in our everyday life. So if you've encountered plastics at home, you've probably seen the categories that we use to classify plastics, which is these so-called resin IDs. There are 7 major categories, 6 of which refer to specific polymer resins. So polyethylene terephthalate, high-density polyethylene, polyvinyl chloride, etc. These show up in a variety of different products, such as your plastic bottles. You can see these in plastic bags. Polystyrene shows up in your takeout containers. And then we really group together all of the other niche plastics under resin ID 7. Now, I do want to point out something here. We like to use these resin IDs in terms of this nice recycling symbol, because in principle, this helps us to identify what materials we can recycle. Although, as we'll see, this can be a little bit misleading. Okay, so these are all very common products. As you might guess, the scale of plastic production is enormous to provide all of these products into our everyday life. Indeed, hundreds of millions of tons of plastics are produced annually. Here, I'm going to focus on numbers provided by a management consulting firm, McKinsey, for the year 2016. I want to emphasize that these numbers are in millions of metric tons, where a metric ton is 1,000 kilograms. These are enormous numbers. In 2016, 300 million metric tons were produced globally. This is from a virgin feedstock. So these are polymers that are made from those source monomers. These then turn into polymers that eventually lead to waste, largely because most of the products we make are considered non-durable. These are plastic products that are thrown out in under a year. Think, plastic bags, right? Even our durable goods, so materials designed for construction, most of that ends up as waste. So we're talking about 260 million metric tons of waste per year. And if we look at where that waste goes, the numbers are really quite disheartening. 40% ends up in the landfill, 25% is incinerated, usually for energy, but this contributes to our global CO2 burden from a climate change perspective. 20% ends up in the environment through littering or other unmanaged dumps, and only 16% is even collected for recycling, of which 25% is then lost. So we only have 12% of our polymers re-enter this production phase via recycling. And almost all of that is through a process we call mechanical recycling, which leads to a degradation of polymer properties, decreasing their value. Now, these numbers are absolutely massive, so it's very hard to conceptualize what 1 million tons of plastics even looks like. So to help you out, here's a photo of a woman standing in what we call a plastic bale. You can see these in terms of these cubic, highly compressed plastic cubes, or really rectangular species. Each of these weighs about 1/2 of a metric ton. So imagine 600 million of these plastic bales being produced per year. Okay, so there's a massive scope of polymer production. Well, this is global, right? And we see that there's this really rough 20% of this plastic production is ending up as waste that goes into the environment. Well, maybe the US is doing particularly well. Unfortunately, we are not. And in fact, the United States is actually the largest generator of plastic waste in the entire world. And our numbers look particularly bad when scaled per capita. So we're producing per capita almost 3 times the waste on average of the 28 European Union member countries. Although to be fair, they're down to 27 now. This is slightly older data. And we're especially bad per capita compared to other large industrialized countries like India and China. Even worse, much of our waste is ending up in coastal environments as litter. So we're talking about millions of metric tons in the year 2016, the same year in which these global polymer flow data were collected, that ends up in the environment as microplastics, nanoplastics, some of these terms you might have heard in the popular press, largely due to illegal dumping, littering, or mismanagement when we export polymers and plastics for recycling. Okay, so really there's tremendous environmental side effects at scales that are very difficult to imagine. So now let's zoom in a little bit. Let's think not at these global levels or these countrywide levels. Let's think about the plastics or the other recyclable materials that you put into your recycling bin every week or at your office every day. What are the rates of recycling for those materials? So we can pull statistics from the Environmental Protection Agency. This is for 2017, so relatively recent data. And we would find that if you look at all of the municipal solid waste that's collected in your recycling bins and brought to what's called a materials recovery facility for recycling, only 25% of that is recycled. That number is not great, but if we look at different categories, you might see these numbers are actually reasonably high. Paper and cardboard are recycled at quite a high rate. Steel, not so much, aluminum, not so much, but other metals go up to 66%. The US recycling rates of plastics is only 8%. So we can break that down into a table. This is data back to 1960, again, from the EPA. If we look at the latest year for which we have data, here's this massive 36 million metric ton production rate. Less than 10% is actually recycled. The vast majority is either incinerated, contributing to global CO2 numbers, or ends up in the landfill, okay? So we're really not appreciably recycling any of the plastic that goes into our recycling bins. We can break this down even further by looking at specific rates with respect to the 7 plastic resin IDs I referred to before. So here they are. Each of these numbers in blue is the amount produced per year. This is from a slightly earlier year, but the numbers haven't changed. This is the US recycling rate. You can see that even though this has a nice recycling symbol for resin 3, we are literally recycling 0% of the polyvinyl chloride that's produced in a given year. The numbers aren't much better for your polystyrene or polypropylene. Now there's numerous reasons for this. Some of them are just economic. Only recycled PET, which is 1, HDPE, which is 2, and polypropylene, which is 5, they're the only ones that actually have markets for recycled materials. There's just no way to sell the material we get from recycling. In Wisconsin, only resin IDs 1 and 2 are required to be recycled. If you've been sorting out other numbers, it's unlikely that those have been recycled at any point. There are some products that have high recycling rates, but even these high rates for plastic bottles are still much lower than the rates of metals and cardboard and paper. So we urgently need new technologies to improve these recycling rates. So you might be asking, well, why are these so hard to recycle? So it's worthwhile to look at sort of existing recycling technologies and the infrastructure that's been built up to handle these materials. So I referred to mechanical recycling before as the #1 technology used for polymer recycling. This is a schematic of what would be considered a simple mechanical recycling process. I can imagine collecting my plastic waste, putting it in a centralized facility, and then sorting out materials on the basis of their resin IDs. Maybe I take out all the plastic bottles. Well, I want to create polymer resins, for example, so I can imagine just grinding these up, washing them to remove contaminants, maybe grinding them again, and then getting flakes of plastic that in principle should be very similar to the polymer resins that I started with, and therefore could be used as starting material to remake my product. In principle, this sounds good, but the problem, amongst other problems, is that all this grinding and washing will irreversibly change some of the properties of my initial material. So I generate less valuable products that cannot be remade back into the initial plastic bottles, but generally are destined for applications that have a lower economic value, things like building materials or construction materials. So economics plays a role here. This is what we consider a downcycling process. I'm reducing the value of my materials. That's if everything works. The other challenge is that some of these steps are certainly not as easy as we might illustrate. Consider sorting, for example. How do I actually sort recycled plastic or plastics out of your recycling bin? Particularly when we think about the US, where most of our recycling is now single stream, particularly in well-populated municipalities. So the way this happens in practice is at enormous facilities called materials recovery facilities, sometimes called municipal recycling facilities, but generally referred to as MRFs. This is a schematic, or sorry, a picture of a MRF. You can imagine large amounts of mixed waste being dumped on conveyor belts directly from the garbage trucks that swing by your house, and they get passed through an enormous amount of machinery. This is a schematic from a MRF in the UK, but the technology is pretty much the same in the United States. What happens is all of my waste gets fed into a variety of different operations, each designed to essentially sort out a different type of material. The very first stage often involves human intervention, people hand-picking out materials that cannot be easily recycled, like plastic bags. Plastic bags, for example, will essentially gummy up all the machinery downstream here. We then go through increasingly complex operations to try to pull out things like ferrous metals using magnets. We can use air classifiers to pull out glass based on density. All of these various different technologies are going to have some error rate associated with them. At the very end, we can do something like optical sorting to try to get these giant plastic bales that I showed a few slides ago. So this is much more complex than the term sorting might suggest. And it's really motivating, or really the challenge here is that we're motivated to have all of our recycling commingled, but that really poses challenges when we think about how to deal with it. Now, the challenge is even further than this. This doesn't work perfectly at all. Let's take this optical sorting step. Now I'm going to imagine we have an up-to-date sort of next generation spectroscopic sorter. Okay, so I have a conveyor belt that feeds my plastic waste. It's analyzed using infrared spectrometry, where polymers can be analyzed in real time and sorted with an air jet. This is really nice technology. The problem is my different commingled polymers all have very similar spectral signatures, so they can't be always 100% distinguished from each other, even with automated technology. Okay, so we're dealing with challenges now that are really getting down into the granular level. The other major challenge that we have to deal with is contamination. You'll probably seen these guidelines in your municipalities about what can and cannot go into recycling. These are often very confusing, and it relies on consumers to make good choices about what to put in the recycling. Anytime you put things like food into the recycling, now you can jeopardize the likelihood of your bin actually being recycled, because food that ends up in these recycled materials can compromise the ability of those materials to be reused in food applications. So for example, in packaging applications. Other challenges, as I alluded to before, are things like plastic bags. If you put plastic bags in recycling, you might end up removing a lot of that recycling from your input stream, because that bag has to be thrown out lest it accidentally gummy up the machinery, right? So there's many contaminants that could end up in here. Those contaminants can even include other polymers. So if you recall, Resin ID 3 was polyvinyl chloride. The chloride indicates this polymer contains chlorine atoms. Those chlorine atoms can come out during recycling processes as hydrochloric acid or as chlorine gas, which poses toxicity challenges and can also degrade machinery. So even polymers can be a contaminant within mixed plastic waste. Okay. Now, as if this isn't bad enough, one of the other major problems is that the largest single sector for the usage of plastics is the packaging industry. We've all used plastic packaging, right? You've eaten your yogurt or you've unwrapped your sandwich at the store. The problem is this comprises 40% of the usage of all plastics in the United States, and many of these plastic packaging materials are what are called multi-layer plastic films. This is a schematic of a multi-layer film. As the name suggests, here we have multiple polymer components arranged into layers that are all attached together, right? When you look at your saran wrap, you don't see multiple layers associated with it. These layers are selected because each different layer confers some specific advantage. I might have some layers that are barriers to oxygen, for example, so that my food maintains its freshness. I might have some that are selected for rigidity, so that I get a certain stiffness to my plastic packaging. For example, if I'm buying yogurt, right, I want a stiff base to my yogurt container. Well, now I have all of these different polymers, and they're commingled essentially at molecular length scales. They're actually tied together, adhered together. So now I definitely can't use mechanical recycling. So plastic packaging is a major issue. Worldwide, only 14% of this largest market segment is recycled. Okay, so I think I've just spent 20 minutes convincing you that it's hopeless and that plastic recycling will never work, and we're producing way too much of this material, and the only solution is to ban it, which is not economically going to happen anytime soon. But don't worry, despite how discouraging it is, I think that there are reasons for optimism, and particularly in the context of the new technologies that I'll be discussing in just a few minutes. But I think it's important just to highlight a couple of the policy changes that have really motivated some of the interest in plastic recycling. Perhaps the most notable one, and I'm certainly not a public policy expert, but in my opinion, one of the most notable ones happened in 2018. So if you were to look at that 2016 graph again, what I didn't show you before is that the major importer of plastic waste for recycling is China. Through 2016, China had imported more than 50% of all of the waste that was exported by other countries. And this is because China has an extremely robust recycling infrastructure. They really have it all figured out. They're producing all these products that are sent via ship to, let's say, the United States to deliver manufactured goods. Those ships are then loaded up with waste and sent back to China, where they can take advantage of the country's infrastructure to recycle them. So the recycling rate of China is actually quite high. The problem is, because of the growth of plastic production, China decided that in order to meet its own environmental goals, they had to greatly limit the amount of plastic they were importing. So in 2018, China implemented what's called the National Sword Policy that banned the import of most plastic waste. This had a tremendous impact. So here what I'm showing are a diagram illustrating the materials flows into China from the 43 countries that exported waste there for recycling. Okay, so this is a global impact. The larger exporter, of course, was the United States. Within 1 year of the implementation of this policy, plastic waste imports dropped 99%. And a conservative estimate is that this will lead to 111 million metric tons of plastic waste that has to be sent somewhere else because it would have been sent to China by 2030. So that's within 9 years. These are huge numbers. So because of this change, there's been a massive investment in the recycling technologies and infrastructure to sort of make up for the waste that would have been recycled in China. So this is why I think there's some optimism. If we look at what the European Union is doing, for example, you may have seen a headline just a few days ago, which emerged from what was occurring in 2018 when the European Union launched their plastics recycling strategy. Their goal was to get to 50% recycling of plastic packaging. Again, that's almost 4 times what's happening in the United States by 2025. In 2018, the EU was already at 3 times the rate of the United States. So they've been trying to increase that number and have been doing a really good job at it. They also require all plastic packaging to be recyclable by 2030, 90% of plastic bottles to be recyclable by 2025. These all look achievable. 3 days ago, they banned the 10 most common single-use plastic items. These include things like beverage containers and takeout containers. So the EU has really been a blueprint for the type of policy changes that can happen in the United States. To the US's credit, right now, there's a series of bipartisan policies that are moving through the Congress, a little bit slowly, but these include things related to funding for waste technologies, as well as improving the communication about recycling practices, things like those schematics about contamination, right? So how can we both inform consumers while also providing for new technologies? Now, in terms of R&D, in 2019, in response to some of these changes, the US launched what's called the Plastics Innovation Challenge, spearheaded by the Department of Energy. This was a coordinated effort to unite a variety of funding resources directed to both universities, the national laboratory system, as well as public-private partnerships. Okay, earlier this year, they put out a roadmap identifying the specific technologies that the US will invest in to become a leader in deploying and developing technologies to minimize plastic waste. What's interesting here is they identify both near-term, medium-term, and long-term targets to try to hit the goal of becoming a leader in plastic recycling by 2030. Now, as part of this, we were funded through this Chemical Upcycling of Waste Plastics Center to address several of these different target goals. This includes one goal, which is developing technologies for deconstruction. How do I take plastics and break them down into their constituent components? We're also going to target upcycling. It's in our name. How do I take plastics and during the recycling process, instead of decreasing their value, which is what happens with mechanical recycling, how can I instead increase their value by converting them into even more valuable products than they were originally? How can we also develop technologies that will be scalable and deployable, right? Inventing something in the lab is not enough. We need these materials in the near term, these technologies in the near term to be able to reach our industrial partners and actually be deployed in the real world. I also want to highlight that recently, 2 of my colleagues in chemical engineering, Professors George Huber and Victor Zavala, also received $2.5 million as part of a team to investigate biodegradable polymers. This addresses the 4th plastics innovations area of recyclable polymers by design. How do we start replacing the polymers identified by those 7 IDs with polymers that actually will degrade in the environment over shorter time spans? Okay, so here at UW-Madison, we're really targeting all aspects of this plastics innovation roadmap, and I'll get into that in a bit more detail now. All right, so that was part 1, stating sort of the scale of the problem and the challenge. Now let me tell you a little bit about what we're actually doing in terms of the technologies that we're developing to address plastic accumulation and the plastic waste challenge. And I'll try to keep this at a fairly high level, but I'm happy to answer technical questions afterwards. So again, I'm a representative of CUP, so the Center for the Chemical Upcycling of Waste Plastics. So briefly, we've received $12.5 million of funding over 5 years to unite efforts across 7 different universities, 4 of which are in the US, 2 in Mexico and 1 in Canada. We also are working very closely with industrial partners because, again, a key goal for us is to make sure that our technologies can actually impact technology, right? This number of industrial partners is actually growing every day. We're very excited to ensure that we have buy-in from industry who can help us make a real impact. Before moving into CUP, I want to define 2 more terms for you, which is what we call post-industrial waste and post-consumer waste. Now, up until now, I've been talking about post-consumer waste. So the waste that all of us generate and is collected in our recycling bins and taken to those MRFs. There's also a substantial amount of waste that we call post-industrial waste. This is waste that's generated as a byproduct of a manufacturing process. So again, I imagine I take my yogurt container, it's a weird shape. I probably cut that out of a roll that was originally rectangular. And in doing so, I generate all these scraps that are of known composition, that have never been in contact with contaminants and are collected in a single manufacturing facility. That's what we call post-industrial waste. That's an ideal target for recycling. Most of it currently goes to the landfill. So CUP really has 2 key technologies that we're developing. One that we call solvent-targeted recovery and precipitation, or STRAP. That's targeted at this post-industrial waste. And then the other is called pyrolysis, which is targeted at this post-consumer waste. So we like to tie this together through a single chart that highlights the technology infrastructure for chemical recycling, okay? I've already told you a lot about this current technology in green here, where we take post-consumer waste, we sort it at a MRF, we send it for cleaning and then mechanical recycling. Our vision is to say, can we now take post-consumer wastes, sort them, send some of them for this catalytic upcycling via pyrolysis, and some of them for recycling via the STRAP process, while simultaneously taking our post-industrial waste and recycling them via the STRAP process. If this works, we now have technologies that can address all sources of plastic waste and can fit in with existing technologies in the recycling infrastructure. So let me now tell you about each of these 2 technologies in turn, starting with the post-industrial waste process that we call STRAP. All right, so here's the schematic of the STRAP process. And if you're interested in more of the technical details, I'll direct you to our Science Advances paper, which was published in 2020. This is an open access paper that anyone can download for free. This technology, which we developed in partnership with Amcor, the world's largest manufacturer of multi-layer plastic packaging, is based on a very simple idea. Let's imagine I have a multi-layer film and I know what it's made out of. Okay, so here I'm showing 3 common plastics that comprise many multi-layer films. The basic idea is I want to take my multi-layer film and I'm going to put it into a liquid that we call a solvent that is designed to selectively dissolve only one of the components of these multi-layer films. In other words, I can imagine I'm cooking up it's like I'm taking boiling water, I put my plastic into that water, and only one of the components actually is dissolved in the boiling water. Okay, probably many of you have heard of the concept of like dissolves like, or you've used acetone to remove inks, all the same concept. We're selectively dissolving just a particular component on the basis of its chemistry. Then what we can do is we can filter out the remaining components, and we can add something called an anti-solvent, which is the opposite of what we added in the selective solvent. This is a solvent that is not going to dissolve the polymer that it dissolved previously so that it comes back out as a solid. Okay? I do this for each of the different components in turn. So I dissolve a component, I filter out the remaining solids, I then add an anti-solvent to get the component that I originally dissolved. This allows me to get every single one of my layers. The key challenge here is, how do I choose these particular solvents? How do I choose the temperatures? And how do I make sure that this is economically competitive? So the team that we've developed at CUP is spread across the University of Wisconsin-Madison, Iowa State University, and Amcor. And we're dedicated to really answering 4 questions as we think about designing STRAP processes for common multi-layer plastic films. The first question, the one I'll tell you the most about, because this is the one I'm directly involved in, is what solvent should we choose to both selectively dissolve a film and then precipitate it back out? The second question is, once we choose these solvents, do they actually lead experimentally to 100% recovery of the polymer components that I want? The third question is, can this process be economically competitive? Will we be able in the near term to convince people to use this recycling technology so that I can address concerns related to market size with recycled polymers? And then the fourth question is, once we have these recycled resins, are they actually suitable to be reused? For example, could they be used to remake the same films from which they came, in which case I have a truly circular recycling process where I'm taking the material and recreating the source material again that I could use back in its original packaging application. So I'll just step through each of these different questions in turn, starting with the first, which is how do I choose solvents for dissolution and then precipitation? So dissolving a component and then getting it back out. So we use what we call a multifidelity approach that uses computational methods to look through the large space of possible solvents that we could choose for this problem. I'm not going to go through the details here, but suffice to say that there are hundreds of different solvents in common industrial use. We have an internal database of over 600. Many of those solvents can be mixed with each other. So I can start to have a search space of possible solvents that's effectively infinite and way too large to be searched using experimental screening alone. So we use a multi-step approach where we first measure what are called Hansen solubility parameters. These are tabulated experimental parameters to characterize the interactions between a polymer and a solvent. Explicit molecular dynamics simulations, which is essentially like a computational microscope that tells me a lot about how molecules interact at nanometer length scales to drive dissolution. And then a quantum chemical calculation technique called COSMO-RS that I'm not going to talk a lot about, but it basically allows us to screen through solvents very rapidly. Once we screen through the thousands of different possible solvent combinations and find ones that seem suitable, we can also then ask questions like, which of these are going to be toxic to handle and therefore shouldn't be used in a recycling process, which are going to be cost effective, et cetera. So let me just give you a snippet of one of these computational techniques, which is explicit solvent modeling using molecular dynamics simulations, because the concept underlying this is quite straightforward if you can remember back to high school physics. So in high school physics, we learned Newton's equations of motion, so force is equal to mass times acceleration. And in molecular dynamics simulations, we use those same equations of motion, but just at the level of individual molecules. So here I'm showing the output of a simulation as a video. Each of these cyan balls we treat as a particle that moves according to Newton's equation of motion and represents a carbon atom. Each of these red balls represents a hydrogen atom. The background here represents a solvent called dimethyl sulfoxide. So this is a video through the computational microscope of my polymer, a very small chunk of a polymer, essentially wiggling around in the solvent. What we can infer from the interactions that we observe in these videos is how soluble that polymer is, right? So we can learn something from these simulations about the affinity of the solvent for the polymer, or in other words, does like dissolve like in this particular case. We can do this thousands of times. We can use that to generate computational predictions of the solubility. In other words, how much of that polymer can I dissolve in that solvent? We can then validate these predictions against experimental measurements performed by Professor George Huber and his student Kevin Sanchez Rivera. So here, for example, are just 9 common solvents at various temperatures where we can measure the solubilities of polyethylene or ethylene vinyl acetate. This is a common component of plastic packaging. On the right-hand column, I'm showing our predictions from simulations. On the left hand, I'm showing experimental measurements. So we see pretty good agreement, and especially in terms of figuring out which of the solvents dissolve these to a very high rate and which dissolve them to a very low rate. In other words, which might be appropriate for selective dissolution and which might be appropriate as an anti-solvent. We can also do this as a function of temperature, where again, we can validate computational predictions here in blue against experimental results in red. We see a slight overprediction, but all of the trends are the same, and that's really all we need to identify the best solvents. Okay, so now that we have these computational tools, we can start to design recycling processes for the scrap process. So for example, we could identify that for a given film provided to us by Amcor, which is one of their highest volume films that is currently not recycled at all, we can apply our computational tools to identify solvents, anti-solvents, and temperatures at which the solubility of one component, for example, polyethylene, is very high, and the other 2 components, EVOH and PET, is very low. So if we go and put our film into this solvent at this temperature, about 100 degrees Celsius, I should only be dissolving the PE, which means that now I've selectively recovered that. I can add an anti-solvent to take it back out. So we can use this to design these processes where I imagine taking my film, dissolving that for a certain amount of time to get my PE, recycling that through an anti-solvent, and then recovering the solvent that I used to minimize my costs. I do this stepwise for each component of my film. Now, this is what we can design computationally. We can then ask Kevin, the student from Professor Huber's group, to go into the lab. He can do these at bench scale. Again, these are grams of material, so not tons. This is just a picture of his lab setup where he has these things dissolved. And what happens is we end up getting nearly 100% of the original material in our film. These are images just to demonstrate that. At the top, I've just shown you a physical mixture where I'm essentially just mixing my different polymer components together so I can measure 100% recovery of each of these different components by doing the strap process. This is the actual multi-layer film provided to us by Amcor. For IP reasons, I can't tell you the exact composition of the film, but if I look at the yields of each of my different components, I would find that they're nearly 100% of what Amcor tells us is in it. So this addresses the question of how do we choose solvents and does experimental recovery work? We can next use spectroscopy to see, are our materials the same as the materials that we started with? So this is the characterization part. If they're the same, then we can reuse them to make the initial films. So these are examples of what we call the virgin resin. So this is our starting material that went into the production of the film. These are the solids we recovered from just mixing the different film components together. And then these are the solids that we recovered from the film itself. You'll notice that these are nearly identical spectra for all three components. The only peak that was different turned out to be because there was another component of the film that Amcor didn't tell us about, which we discovered through our strap process and have now designed in sort of the new iteration of strap to recover as well. So we've got solvents, we've got experimental recoveries. We could reuse these to make films, but is it economically competitive? So the next thing we did is what's called a techno-economic analysis. You can think of this as essentially trying to do accounting on all of the different costs associated with the process. I like to think of this in terms of cooking. If I want to cook some pasta, I have to ask myself, how much does it cost to first buy my stove? How much does it cost to heat up water? How much does the water cost? And at the end of the day, at what rate should I sell my pasta? Okay, that's the type of calculation that we're doing. So to do that, we have to think about every single piece of equipment that would be required to do this process, how much heat is required to heat up, let's say, acetone to 100 degrees Celsius, et cetera. We even include things like taxes, et cetera. And when I say we, I really mean Professor Zavala's group here at UW-Madison. At the end of the day, we can make assumptions about how much material we need for this to be a competitive process. So here's the analysis for the strap process I just demonstrated. We get a minimum selling price. So this is how much we have to sell the material for us to break even, of about $1 per kilogram. This is actually great news because if I were just to try to buy the major component of this film as a virgin resin, it's nearly the same price. So once they get up to 3,000 tons per year, which is still a very small number compared to the amount of post-industrial waste we generate, we find that our process is economically competitive. And moreover, we found that we can even reduce the price if we remove some of these processing steps by using things like temperature changes rather than anti-solvents to precipitate out our film. As more evidence that this is economically competitive, there's a number of companies that are currently commercializing related but not identical solvent-mediated technologies. And these are going to large scales, 48,000 tons a year, for example, in the United States through a company called PureCycle, where they're currently building a facility as of 2021. So we're really excited about strap as a way to recycle these previously unrecyclable multi-layer films if they're sourced from post-industrial waste at high volume. Let me now briefly talk to you about the other technology that we're developing, which is a way of treating post-consumer waste that's gone through a MRF, has been sorted, has been washed, and then can be depolymerized and eventually upcycled to new materials. This process is called pyrolysis. The basic idea is as follows. We take our input plastic waste, and what we're going to do now is we're going to heat this up to extremely high temperatures to do what's called thermal depolymerization. So we're going to take our long chain we had from slide 1. At high temperatures, that chain will break into small fragments as small as the original monomer. This is not the same as incineration because we're not doing this in ambient atmosphere, but rather we're doing this in conditions where there's no oxygen, okay? Now, as I heat up my film and I get these extremely high temperatures, 600, 800 degrees, I will of course lead to vapor phase materials. And those go into what we call this catalyst room, okay? So in here, we're gonna have materials that are designed to direct chemical reactions to produce very specific products that are gonna be of value for downstream applications, okay? So this is an effort being led by Professor Xianglan Bai at Iowa State University, where they're using catalysts called Xeolites, which are essentially porous materials where my vapor can diffuse into them. They undergo a chemical reaction and come out in a different form. And we've shown that these can be used to generate aromatics and olefins, which are classes of products generally obtained from petroleum and are used as precursors to fuels and chemicals. So in other words, we're converting plastic waste into fuel, removing petroleum as a feedstock for that industry. And this would be considered an upcycling application. Can we take the millions of tons of waste in the landfill and use it as a fuel source? Professor Huber's group has shown that we can generate a wide variety of different products here. I'm not going into the details, but again, a key question is cost. So to analyze the cost of this process, Professor Mark Mbar-Wright at Iowa State University did an analysis of what is the minimum selling price of these products based on different assumptions of the feed price. In other words, how expensive is it to get this material from a MRF? We can envision some scenarios where the MRF gives it to us for free or even pays us to take it off our hands. The reason that this is a reasonable scenario is because landfills charge what's called a tipping fee. In other words, a price to put something into the landfill. So as the landfill becomes more expensive, recycling becomes increasingly more attractive, okay? And so that we can see if that at relatively low feed capacities, a few 100,000 tons a year, again, much smaller than the million tons we were talking about before, we can start being cost competitive against the industry. So those are two examples of our core technologies, but there's a series of other researchers in the center looking at other things. For example, Professor Mavrakakis's group in chemical and biological engineering is using detailed quantum chemical calculations to ask, what are the molecular mechanisms by which these polymers break down? You know, if we understand those, maybe we can design better catalysts to control the products that come out of our pyrolysis process. Professor Hermans is asking, again, how do we design these zeolites, these porous materials, to again, control the types of products that we're generating? And then Professor Zavallo, who I've mentioned a couple of times now, is actually another really critical question is, let's say the strat process is wildly successful and we need to start building new recycling infrastructure. Where do we put it, right? If we think about the upper Midwest, do we want to put it near our population centers? How does that impact the logistics of transporting thousands of tons of waste? So these are other questions at a very high length scale. So we go from molecular length scales up to essentially policy type decisions in the center. Okay, so that's really an overview of what we're doing at CUP. And I just want to briefly highlight again some of the exciting work going on in other parts of the country. So this will just be the last few slides here. And I'm not really an expert on all these things. This is not research coming out of our groups, but I'm happy to answer questions about them at the end. So if we go back to that Plastics Innovation Challenge roadmap that I led off with about 20 minutes ago, we saw there were 4 key areas. And we didn't talk about all of them. So here I'm going to talk about some of the areas highlighted in red that are being addressed outside of CUP. For example, mechanisms for biological approaches to destroy plastic waste, or maybe ways to make new plastic films that could replace those that are being commercialized today. So here's some work on plastics that are recyclable by design. Now, the basic idea is simple. Remember that plastics are made of polymers. Polymers are repeated units that I said are chemically bonded together. Well, what if we made units where those chemical bonds were intentionally made to be weak under certain conditions, so I could easily break them up? That's the basic idea of this paper from 2019 from Berkeley, where they made what we call plastics out of dynamic covalent linkages. So these are bonds meant to be broken. When I take the monomers that comprise this plastic and put them together and I grind them up so they're in close association, they'll form polymers. But if I supply acid to the system, I can easily break them up. So this gives me a very simple recycling process by design. So this was an exciting breakthrough, but unfortunately, these polymers are really not similar to the polymers that we use every day. So there was another breakthrough just earlier this year in 2021, where they basically took the same idea, but now they made something very similar to high density polyethylene. Remember, that's Resin ID 2, which is one of the ones that has a market for it. So now again, the idea is I take my non-renewable material, which I have to mechanically recycle and downgrade its material value. Instead, I put breakage points in it that allow me to break it up very easily. Now what I can do is completely recycle my final product back to the initial starting material via these dynamic covalent linkages. So this is the type of exciting work that's addressing some of these challenges where, questions about scale up and industry adoption are still several years away, but really these are at the forefront of polymer design. Okay, what about biological processes? Well, we know that microbial communities are extremely good at digesting things. So perhaps that could be an avenue that we could exploit to break up polymers. Well, that was the idea that led to this paper in 2020, an engineered microbe, really an enzyme, designed to attack plastic bottles made out of polyethylene terephthalate. This is a paper that actually came out of a company called Carbios located in France. And they did two really cool things here. First, they used computational molecular design strategies to try to figure out what specific amino acids at the active site of an existing protein have to be mutated to increase the likelihood that a microbe will break down plastic. So they did computational analysis to try to understand the types of mutations. What they ended up with was an enzyme which can break up PET in a landfill or under any controlled environment. So this is really training and designing bacteria to eat plastic, which is very exciting. Another breakthrough came earlier this year, again from Berkeley. This is Ting Shu's group. What her group did is say, can we actually make plastics that have these enzymes built into them, right? So instead of taking this plastic and putting it into some special landfill that has these microbes as part of it, what if the plastic as designed has an enzyme that'll break it down and basically eat it from the inside out? So they did what are called nanodispersed enzymes. The key technological innovation here was in terms of both engineering the enzyme to be stable within a solid polymer, as well as engineering in triggers, which allow me to activate the enzyme when I want my polymer to be dissolved. So this is another exciting where we can sort of leverage biology's capabilities for eating things and bring them towards the plastic problem. Finally, these were largely academic efforts, but I also want to point out that there's a lot of exciting work in startup companies and industry across the world. So here's a particularly exciting one I want to highlight that goes all the way back to that challenge of recycling and MRFs. So this is a company called Robotics, which is developing AI-assisted technologies to improve sorting. So I have a video here, if it plays, which shows their technology. Okay, so this is their robot arm, which has been trained using machine learning algorithms based on image recognition to try to pick out specific components of municipal solid waste, which you can sort automatically. This is very exciting and is another way to get, again, highly pure input streams that could be fed into our strap process or fed into pyrolysis or what have you. Another thing we might think of is how do we replace those virgin resins entirely? So something I didn't mention is that most of the polymers that we synthesize today come from petroleum as the original virgin feedstock. Well, a company that spun out of UW-Madison and was supported by the Wisconsin Alumni Research Foundation is called Pyran. Pyran's goal is to instead take biomass, so be it wood chips or corn stove or what have you, and convert these into polymers to replace the polymers that are being used industrially, or at least to create the same polymers that are being used industrially from a renewable feedstock. So right now they already are leaders in producing new adhesives, coatings, and paint. And we're very happy to say that the founder of Pyran is a recent graduate with a PhD from our department. Okay, so these are just examples of the other types of technology that are being developed to address the plastics recycling problem. So with that, I want to summarize by just highlighting a few key points. There's a massive scale to plastic production, over 400 million metric tons annually per year, and less than 10% of the plastic waste generated in the US is actually recycled. But since 2018, there's been massive investment in infrastructure and recycling technologies that is likely to continue. We're fortunate to be the recipient of some of this grant funding. We're using this to develop two key technologies targeted at post-industrial waste, where we can recover the components of previously unrecyclable multi-layer films, as well as chemical processes to convert the byproducts of municipal waste into new products to compete against petroleum. Beyond CUP, there's investigators worldwide that are really developing cool technology, and hopefully this helps you to see why some of these news articles from the very beginning are so excited about the potential for future polymers to replace our existing resins. So I want to highlight just a few things here. These are the principal investigators in CUP that are at UW-Madison. We also have a number that are at other universities whose work I didn't highlight to as as much a degree. If you want to learn more about the center, we recently launched a website, cup.org, as well as we have a Facebook group where you can follow up on cup research. And you can also read about some of the work that individual students are doing in their stories. For the sake of time, I didn't highlight particular students so much, but hopefully you saw their pictures when I presented that earlier. So with that, I want to thank all of you for your attention. Thank the Department of Energy for providing funding. And I'd be pleased to answer any questions that you might have. Thank you.
Thank you very much, Reid. Fantastic stuff happening. Bia, do we have any questions in the chat yet? I think we have one comment that you might want to draw attention to.
Yeah, Brian Johnson put in the chat, here's how the recycling is sorted in the city of Madison by the waste system. And he has a video link there.
Great.
I have a question.
Go ahead, Wynn.
You mentioned that you have people that are looking at the economics of the total overall process, which is obviously good. But a lot of those processes involve quite a bit of energy generation. Are you looking at the carbon impact on of that type of recycling that you're?
Yep. Yes, thank you, Wynn, for that question. It's a great question. So as part of the techno-economic analysis, we also perform what's called life cycle analysis and so there's really two different analyses here. There's essentially how much does everything cost? To calculate that, we actually have to calculate energy consumption, because that's actually one of the major drivers of the cost, particularly for our operating costs on a year-to-year basis. So we get that information. We also can do life cycle analysis to understand, where the materials, where the input's coming from, where the output's going. So we can also learn things about, what is the actual amount of material that we might divert from landfill, for example. So we have all that information. This is actually a less energy intensive process, STRAP I'm speaking of. I don't know the numbers off the top of my head for pyrolysis, but it's less energy intensive than creating the source material. And that's really the process we're competing against. And part of this, again, is because the source material is coming from petroleum feedstocks, then have to go through chemical synthesis processes. Here, we don't have to synthesize anything, right? The only energy input is really through the temperature that we use for the initial dissolution stage. We can actually bring down some of those energy costs by removing anti-solvent and so forth, because that reduces some of our steps. So fortunately, reducing energy usage and minimizing economic cost are aligned in this particular case.
Thank you.
Yeah, thank you.
Bia, go ahead and read the next question from the chat, and we'll go back and forth between spoken and chat questions.
Sounds good. The next question is, what technology is China using, and why can't the US just duplicate their system?
Yeah, so it's not that there's particularly robust technologies in China that are better technologies than the rest of the world. I would say that most of the adopted technology, to the best of my knowledge, are based on mechanical recycling. It's more that there's challenges with logistics in the US. So for example, there's only a finite number of materials recycling facilities, recovery facilities, MRFs, and it costs a lot of money to transport materials in between them. China has this robust infrastructure where it's actually cheaper to send materials overseas through shipping than it is to ship them 2 states over for recycling. So it's not that the technology is different, it's really that the infrastructure is set up to recycle in a much more efficient way.
Does anyone have another spoken question they'd like to ask? If not, Bea, why don't you go on to the next chat question?
Are we generating microplastics when we dissolve and reconstitute plastics? Would enzymatic degradation do the same?
Yeah, so let me first clarify what microplastics are for those who aren't familiar. I didn't talk about this all in my talk. There's been a lot of concern, well-founded concern, about the idea that many of the plastics that are leaked into the environment, so for example, that enter our coastal waterways, actually break up to some extent. And so you've probably read these things about microplastics you ingest in your body because they've entered the environment and are broken up via natural processes. We've also called these nanoplastics, depending on the scale to which they're broken up. So when we dissolve plastics using the STRAP process and reconstitute them, there's no chemical reaction occurring, and therefore we're not generating microplastics. A lot of the microplastics are generated over very long times under these sort of extreme conditions, right? They sink to the ocean, whatever. Enzymatic degradation tries to go a step even further, right? Where it's actually trying to break it down to the original monomer, which can then be subject to another chemical reaction to build back up the polymer. So in principle, if all these processes are successful, of course, we would not be generating microplastics. We'd actually be going from the full polymer either to the monomer or from the full polymer back to the full polymer without an intermediate step of something in between. But that's a great question.
Thank you. Any spoken questions?
Yeah, I have one.
Mark, go ahead.
Yeah, so in your reaction layout, you showed reaction times that seem to be long, such that it'd be hard to keep a waste stream moving quickly and process a lot of material if it actually takes a lot of time. This could partly be reduced by chopping polymers into smaller pieces, but then that's doing more mechanical disruption. Also, attendant with the solvent methodology, you have to recover the solvents that are going around and around. And you probably have losses, and then you have to dispose of contaminated solvent with some mechanism that's safe for the environment. Can you comment on these items? And I guess there's one more. It seems to me there's a lot of work in using feedstocks of wood chips and corn stove or other cellulosic materials to make truly compostable polymers, such that the polymers escaping into the environment will readily disappear in a safe manner.
Yes, I can comment on all three of those things. So first is the question about essentially what we'd call dissolution time. So, in our process flow diagram, as you correctly noted, we had dissolution times in the order of hours for small amounts of polymeric material. And you're exactly right. This could be reduced by essentially increasing the surface area to volume ratio of our materials by grinding them up using existing mechanical recycling technologies. So that's actually built into the techno-economic analysis. We just don't demonstrate that at lab scale because those technologies are already mature. But remember, this is based on post-industrial waste streams. So we don't mind doing the mechanical recycling here because we don't have to worry about contamination. And in fact, there's actually shredders that are being developed by our partners at Michigan Technical Universities that can shred these to extremely fine, fine pellets. Pellets isn't quite the right word, very small amounts. So that was an astute observation. The other thing I would mention is that we are working on how to make this a continuous process as opposed to a batch process. Right now, the technical challenges have been largely in solvent selection, but as we begin optimizing these processes during scale up, we'll be much more careful about timescales associated with dissolution as we move to these two continuous processes. So then your second question was about, or your third question, because I remember that one. The third question was about, how do we make polymers from biomass, right? Cellulosic biomass, even lignin-derived polymers. We take advantage of these feedstocks. That's exactly what the funding from DOE to the Huber and Zabala groups is designed to do. I pointed at this a little bit earlier. In fact, a lot of the biomass deconstruction community has kind of converted to this question of how do we, make new polymers or use those techniques to disintegrate plastic waste. So there's absolutely a lot of effort there, including here at UW-Madison. We have a rich history in biomass. But the question is, can we make polymers that actually are either replacements for existing polymers so they can enter the market, or can we find particular markets where they're going to be valuable? And so that's also what Pyran is really doing in terms of its biodegradable polymers as well. The second question was about solvent recovery. So again, that is something within our techno-economic analysis. The good news is we've mostly been able to use common industrial solvents here. So solvent recovery processes are well established, right? We know everything about their phase equilibrium. We know how to distill them. So we can make, again, very good estimates about solvent losses, process, and most of those go into our operating costs. So you're right that the solvent is a big question, but as long as we stick with solvents that are industrially accepted, we have good bounds on the costs associated with them. In terms of making these more environmentally friendly, well, another thing that we can do now that we have a computational methodology to look at hundreds of solvents very quickly is we can start using solvent guidelines about the greenness of solvents or the environmental friendliness to look for replacements. So for example, here at UW-Madison, our favorite green solvent is gamma-valerolactone, which came out of a lot of work in the biomass community. It can be developed from biomass. It can be used as a drop-in replacement for many of the common polar aprotic solvents used industrially. So those are great questions, and are really questions, I think, targeted at how do we evolve our technology and optimize it for industrial usage. And those are definitely things that we're thinking about. So thank you for your question.
Mark, do you have a follow-up?
No, those were excellent answers, and they're looking at this in great detail. I'm an MIT grad also, by the way.
Oh, great. Of course.
Well, I finished in 5 years with 7 and 16. That's biology and aero and astro.
Fantastic.
Yeah.
Thank you, Mark. Any other, or I guess if we're back to the chat questions, Bia?
Yeah, first Sandy Rotter put in a comment about Virant and has some links to some articles there. But then the next question is from Peter, who asks, can the microbes that chew up plastics be dangerous to our society that is already mostly built using plastics?
Yeah, that's an interesting question. You know, I think, again, most of this has only been demonstrated at lab scale, right? So it's unclear, you know, I remember this old Kurt Vonnegut, like Ice 9 type of scenario where, you know, you have your material that takes over the world. I didn't actually read the book, but my dad told me about it. But, you know, so you might be envisioning something like that. I don't see that as being an issue because really the degradation timescales right now are still long compared to, you know, I think you'd notice your building degrading. Right now, these are the types of microbes that are still being built in the lab or engineered in the lab. And the idea is to introduce these to landfills. But honestly, that's not my area of expertise, so I can't speculate beyond that.
I'd just like to comment that in many cases, for example, I remember people were worried about Teflon taking over the world because there was nothing to break it down. And then they found a microbe that would use it for basically for an energy source. But in many cases, these kind of microbes that are attacking these types of materials, you know, normal environment that's not controlled, they tend to get outcompeted by microbes that are using far less arduous processes. So it doesn't seem very likely that you know, one of these would get out and eat all the plastic in the world.
Thank you.
Thank you, Wynn. I've got a couple questions about the EU ban. I didn't see plastic bags included in there, and I was wondering, had they already banned plastic grocery bags? And we use a lot of silo bags in Wisconsin, and I'm wondering if those kinds of things are targets of what your work are doing, that huge amount of plastic that goes into a silo bag, and then the itty bitty but huge amounts that go into plastic bags.
Yeah. So for the EU plastic ban, I actually don't recall exactly what all 10 items were. The problem right now is that single-use plastic bags are so ubiquitous that it's hard to completely ban them just from a legislative perspective. In the US, there's actually a call from the Department of Energy right now. We've actually put some proposal in, so fingers crossed, which is targeted specifically at single-use plastics like plastic bags. So there's certainly interest in developing technologies there. I don't remember exactly what the EU did, but I'd be happy to get back to you about that. And I think that also gets to your second question, which is no, we haven't addressed that particular class of materials so far, but the strap process that we're describing can easily be applied to plastic bags. In fact, one of our scale-up challenges that we're thinking about as we think about other technologies to complement strap would be, can we use solvent-based materials that both are solvent-based technologies that actually separate out particular products? So if I know that my plastic bags are primarily made out of a certain resin, right, could I actually design solvents that are aiming to take those out of my stream before passing that entire waste stream off for mechanical recycling? So I take the human out of that first step of the MRF. So those are kind of aligned with some of the technologies we talked about today.
And then for the silo bags, are you familiar with what I'm talking about? Those?
I don't think so, no.
So if you drive out in the country around dairy farms, instead of people putting lots of silage into vertical silos now, many of them are in bunkers, and some of the bunkers are actually just, they look like big white sausages made out of plastic. And then you ferment the silage in that, and then you gradually open the bag with an end loader. And so it's very impressive, huge to me, tubes of plastic, 10, 12, 14 feet in radius, diameter. And it's interesting to me what they do with the plastic. It's probably a tiny amount compared to overall plastic production, but those big white plastic sausages on the ground are amazing to a guy like me that grew up with silos. Brian Johnson is saying ag plastic info. He's got a Marathon County solid waste link there. So thank you very much for that, Brian. Bia, any other questions that you'd like to ask from the chat?
Yeah, one more from Roxanne, who says, thanks for your research. So great. It is happening here in Madison. And then she goes on to say, any consideration of furthering research on upcycling or pyrolysis of tires?
Yeah, so that's a great question. So tires would fall largely as elastomers, which are actually rubbers. So that's not one of the major plastic resin IDs that I discussed today. Because this is not a focus of our sort of near-term effort in the sense that we're mostly focusing on the major resin IDs for which we can identify markets because we're focused in cup on near-term adoption. However, I will say that there have been funding opportunities specifically targeting tires. So I'm not aware of that being in the near-term plan for the pyrolysis folks here at Wisconsin, but it's certainly research that's being invested in elsewhere.
Thank you. Any other questions anyone would like to speak?
Yeah, I just thought of another one, and that's microparticles from textiles. This is a huge problem. We hear about these microfibers everywhere, and we all are contributing to this every time we wash our clothes. So I don't think we can stop washing our clothes, but can you comment on this problem? This is a massive issue. And it's because of the polymeric composition of modern textiles. I understand the industry is seriously looking at ways of modifying even the process of making the threads that go into cloth can greatly reduce the losses of microfibers during normal usage. Do you have any insights or comments on that?
Yeah, I think I'll first say that you've actually helped me remind me of a point that I did want to make throughout the talk, which is that it's great to hear these questions because from talking to our industry collaborators, consumer interest is one of the major drivers of industry investment in plastic recycling. So it's fantastic to hear that you're aware of these. I mean, you are probably more aware than the average person, but it's great to hear that there's so much interest in what industry is actually doing because we know for a fact that this is driving their decision-making, consumer preferences for recycled material. So within this specific context of textiles, I don't know a lot about textile industry myself. However, I am aware that there are a few startup companies specifically aimed at recycling the polymer components of textiles. In fact, one of them based out of Europe, whose name escapes me, it might be PureLoop. A lot of these names are kind of similar. But they actually developed a solvent-mediated process specifically for clothing to try to remove some of the polymer components of clothes. So exactly to your point. The problem with some of these companies and why I think our research is particularly valuable is that a lot of times they're using proprietary solvents and so forth. So it's very hard to get information about their exact processes. But I guess all I would say is that there's a lot of interest in the textile industry in particular. This is actually something that's mentioned in a polymer upcycling FOA from the Department of Energy. I'm not an expert in that particular industry, but I know that there's research activities ongoing.
Thank you. I've got a Wally question. You showed the bales of plastic. I'm wondering, is there any suggestion that people kind of follow the Wally approach and actually set those aside in landfills so that sometime into the future, those become easily recoverable so that they can apply the kinds of technologies that you and your colleagues are developing? Or do we just throw those bales willy-nilly in a landfill now?
That's an interesting question. So I was wondering about that Wall-E, but okay, Wall-E, the Pixar movie from 2008. Right. Yeah. So, a lot of the plastic bales are actually destined for purchase. So a lot of the times that is actually material that'll then be used as downcycled material in transformed into some new product. Oftentimes it's ground up or made into building materials. So that's the reason it's baled, is because it's easy to transport. I'm not aware of, large city stacks of Wally-sized plastic bales. It may happen. It's not something I'm aware of.
Any other questions people would like to ask, either spoken or chats? As a plant person, I'm interested in the different spectra, the different wavelengths of light. Are people looking at specific wavelengths of light to see if plastics can be broken down? I won't say catalytically, but specifically at least. Just wondering if that's something that's possible, especially with the new LEDs that are available, and whether that's something that could be scaled.
Yeah, so what I'll say is that light can essentially be used as an energy source to drive chemical reactions. So UV light, for example, can be one of the drivers for some of the reactions that can occur. So, for the scales that we're talking about, as we think about scaling up these processes, I'm not sure how scalable light-driven reactions are. But another way that you can use, like photochemistry, for example, is in some of these intrinsically recyclable polymers that I talked about. So another strategy is to design polymers specifically to degrade under particular wavelengths of light, to your point. Then I can imagine triggerable degradation. I have an intrinsically recyclable polymer that falls apart when I hit it with a particular thing. So that's a strategy that's been shown in the literature. But again, the challenge is, is this scalable? Those are questions I don't know.
Sounds good.
Yeah, a great question.
Thank you very much. Anyone else like to ask a question, type a question?
There's one more question in the chat from Raj, who asked,
Hi, Raj.
For pyrolysis, what was the reason for choosing coal as the heat source?
All right, so Raj, you got me. That was because I chose a graphic that I found online that happened to have coal as the heat source in that particular graphic. So that was really just to demonstrate pyrolysis. I think as we think about building pyrolysis plants, so one of our industrial partners, Nanotech, is building one, for example. I think it's safe to say that there are other energy sources now that are a bit more up to date, like natural gas and renewable sources that could be used as the energy source instead. So no, we're not ideally using coal, but yeah, that was just from that schematic that I took.
All right, thank you very much. I hope you'll come back in 2 or 3 years as your research progresses. This is fascinating insights you're generating.
Thank you.
Next week, folks, we'll be visualizing atherosclerosis with ultrasound. Hope you come back, and I'll turn the YouTube